The second lecture is about, we'll try to cover some basics of linear algebra. And you will see like some of this is, I think, very much relevant to rest of the course. Some of the topics, I think, it might not be that much relevant, but I think it's good to discuss. That will give you like a very good understanding, like which different topics in this linear algebra are actually relevant to the computer vision area in general. Okay. So let me quickly go over like the outline, what all topics we are going to cover in this lecture. We'll start with vectors and what different operations we can perform using vectors. Then we'll move on to matrix, and again, what different operations are there which are done in matrix. Then the next step will be like different transformations which can be performed using these vectors and matrices, which are actually relevant for computer vision, which can be done on images or videos. So some of these basic transformations will be scaling, rotation, and translation. And then finally, we'll have this singular value decomposition, the SVD algorithm. We won't go into detail because, again, just covering that requires one lecture, right? So we are not going to do that. I will just give you insights what this is and how this is useful for computer vision, and a high-level idea like how this can be applied for some of the problems which we face in computer vision. Okay, so let's get started. Let's talk about vectors. Now, scalar, you must all know. If you don't know, scalar, it's just a number, okay, from a real set. And vector is just a list of these scalars. And you can say that, let's say if you have n different numbers, if you arrange them in a row, that will be your vector, all right? So the space you can see here is that 1 cross n, which means that you will have n different real numbers that will form a vector. So basically it's nothing, it's just a set of numbers, a sequence of numbers, which you can represent something like this maybe, okay? And in this case, you can see the bold is like a vector, and the non-bold version, which has a subscript, it's a scalar. It's just one number. So you have all these n numbers, which can form this scalar. Now, this is like a row vector because it's arranged in a row. If you arrange it in a column, you can call that a column vector. Okay, so the way you represent this is, we'll talk about this later when we talk about matrices. The second term represents actually how many elements you have in a row. And the first element represents like how many elements you have in column. So in this case, it's just one. And here you can see that the first superscript here, that's n, which is saying how many elements you will have in that particular column. So in this case, we have n elements, right? But we only have one column. So this is a row vector, this is a column vector. And again, this superscript here, this kind of indicates like it's called a transpose operation. So if you have to convert a column into row or a row into column, you can transpose that vector. So in this case, this is a row vector. If you transpose it, it will convert it to a column vector, and vice versa. Right? Now let's try to understand, okay, we have these vectors, where they can be used. So in computers, you have a lot of data, right? For example, you can have images, or you can have a lot of other kind of data as well, like how your operating system works, right? So when you store that data in memory, that data is saved in a form of vectors, right? So vectors can be useful. Other interesting use could be, earlier we were talking about given an image patch, if we have to represent that like in some form of numbers. So we can use like a vector to represent that image, and we call that feature vector. We'll talk about this a lot in this course. We can use vectors to store pixel values of images, right? So for example, if you have an image, if it's a colored image, RGB, right? So it will have 3 channels. So what you can do is, for each pixel location, you can have a vector of size 3. And that size 3 is for either R, G, or B. So it's like a 3-dimensional vector. And that represents each pixel in that image. Okay, so that could be one way. So whenever you have to store data in memory, these vectors will come in very, very handy. All right, so let's now try to understand, like in the coordinate system, what these vectors represent. And right now, what I'm showing here is Right, sorry about that. I think someone just annotated. Okay. So right now I'm showing you a three-dimensional space here. It has like three axes, X, Y, and Z. And the world which we live in, it's again three-dimensional. It has X, Y, and Z. Of course, we have time as well. So you can say 4 dimensions. But the visual world, it's three-dimensional. But of course, whatever we are discussing, you can easily generalize that to n-dimensional space. So it could be 4-dimensional, 5-dimensional, or n-dimensional. N could be a very, very large number, right? So when we have a vector, that vector actually represents a point in this coordinate system. For example, if you have a vector which has like 3 dimensions, so you have 3 values, so that will be a point in this space which has 3 different coordinates. All right. So let's say your vector is x1, x2, and x3. Then it will be like maybe this point in this space. And it means that if this is your first axis, then x1 represents this distance, like how far this point is in this direction. And x2 represents how far this point is in the second dimension, so till this point. And again, third point represents how far this point is in the z dimension. Right, so all those 3 points represent distances along those coordinate axes. And now that's one use of vector. And let's say this is another point in the same coordinate system. So what you can do is you can just subtract these 2 vectors, and that subtraction will easily give you like the distance between these 2 points. And if you want a vector representation, then the vector will be starting at this location and going all the way up to this point. So this green line here or a green arrow here, you can also see green vector, that is subtraction of x with y. Right? So it will give you something like this. So those are some of the operations, and later when we talk about transformations, you will see like that will come in handy. So let me know if you have any questions there. Now let's try to understand like some other vector operations. The very important, which I think we will use a lot when we talk about deep learning, is norm of a vector. And norm usually gives you like the magnitude of the vector, or you can also say size of the vector. Right. For example, in the previous slide when I was showing you like the point in that coordinate system, right? So in that case, norm could be how far that point is from the origin. If that point is way too far away, it means it will have a very high norm. Okay, so it's kind of giving you the idea of like how big that vector is. And usually you compute norm using p norm, and this will be the equation. It's pretty simple. What you do is you just take individual element of that vector and you raise that to like p, because it's p norm, and then you sum all those values. All right, so this I will be iterated over like all the dimensions of that vector. For example, if it's like a 3-dimensional vector, then this loop will be repeated 3 times. And then you take this 1 over p power. Okay. So Euclidean norm, it's like you can say p is equals to 2. And what you do is you just replace p with 2 over here. And you can see that what exactly we'll do is we'll just square all the values in that vector and add them up, and then just take the square root. Okay, so that's called Euclidean norm. And then you have L1 norm. In this case, like you replace p with 1. And you can see that 1 over 1, you can just ignore this. And again, if you raise some to power 1, you can again ignore that. So basically, it's just adding the absolute values of all the elements in that vector, right? And all of these are like different ways to compute magnitude of a vector. And in some places, one is useful, in some other is useful. The next interesting vector operation is inner product. This is also called a dot product. And so for inner product, you need 2 vectors, and the resultant is like just a number. Okay, so yeah, so we're talking about inner product. We need 2 different vectors to compute an inner product, and the result of inner product is a scalar number. So it's just one value. Okay, so let's say you have a vector y and you have a vector x. So for computing the inner product, what we'll have to do is we'll have to take transpose of one of the vectors. And we are assuming that the y is actually a column vector and x is also a column vector. So we take the transpose so that this becomes a row vector. And then this operation here actually represents dot product. And the value will be determined using this formula. And basically what's happening here is you take the first element of this vector and you multiply that with the first element of the second vector. Okay, so that will give you one value. Then you add that value with multiplying the second element of this vector with the second element of the second vector. So basically you're just doing element-wise multiplication of all the corresponding values of those two vectors and then just adding them up. Okay, so you just sum those up and that's the dot product. Now, if you think about this, if you have, instead of operating on two different vectors, you can also actually compute dot product or inner product of the same vector, right? So let's say your vector was xi, and then what you can do is you can transpose it and compute like element-wise multiplication and just add those values. And if you think about this, this is going to give you like squared value of each element, and you just sum those up. And if you remember like computing L2 norm, so if you square the L2 norm, it is exactly the same value, right? So basically the dot product or inner product of a vector is equal to squared norm of that vector. The other interesting interpretation of inner product is like using the angle between these two vectors, because you know that each vector you can represent as a point in 3D space, right? If it's three-dimensional vector. And you can compute the magnitude of each vector. So these bar represents magnitude. So magnitude of x, magnitude of y, and you can compute like the angle between those two vectors. So this number here will also give you dot product. Okay, this is important because when we talk about transformations, you will see like why this is very much relevant. So if you try to visualize here, let's say A is your x vector and B is your y vector, and let's say the angle between these two is theta, right? So if you have to compute dot product between these two, you can compute the magnitude of A, which will be like a distance from this location to this location, and magnitude of B, which will be distance from this point to this point, and then you just compute cosine of this angle. Okay. Now, a very interesting point here to note is if y over here is like a unit vector, which means the magnitude of y is just 1. Then in this equation, you can just ignore it because it's just multiplication, right? So it becomes x times cos theta, right? So in this case, B is your unit vector. So dot product will become magnitude of A, and then you multiply that with cos theta. So this is kind of projection of A in this direction. If you drop a perpendicular from this point to this vector, so this is 90 degrees, your projection of A will be exactly this distance. And this distance is A times cos theta. Okay, so remember this projection. It will come in handy when we talk about rotation of a matrix. And so that's coming in from dot product, but don't worry about it. You don't have to make any connection, but just try to understand that what a projection is. Projection is just like, what is the magnitude of this vector A in the direction of B? And we can clearly see that it's this distance, okay? Just remember it's A cos theta. And if you look at this altitude over here, again, this distance you can also compute as A of sine theta, right? This distance, and that will also come as handy. And again, this is just coming from like basic geometry, right? You should all know this, but I'm just refreshing you because it's going to come later. So this distance is A cos theta, which is called projection. This is called A sine theta. Again, it's a projection, but it's like a vertical projection. You can say like projection on the normal. Okay. All right. So that was inner product. The next operation we have is outer product. And again, it's called outer product because it's your inner product was giving you just one number. Outer product is giving you a matrix. Okay, so the only difference is instead of transposing the first element here, you transpose the second element. And in this case, you will see that instead of like summing all those element-wise multiplications, those values becomes like values or elements in this matrix. Please don't annotate on the slides. Whoever is doing that. Okay. All right, so yeah, I think that's fine. Auto product, you can just do element-wise multiplication and put those as elements. So we don't have to go into detail of that.